Hello everyone and welcome back to our channel MooTechie. It's great to have all the dairy technologists and students with us for this second class in Unit 2. In our last session, we covered the fundamentals of mechanical separation, including sedimentation and centrifugal force. Today we will dive deep into the principle, types, and theory of one of the most important separation methods, filtration. We are now moving on to the topic of filtration. We will cover its principle, types, rates of filtration, and pressure drop calculations. Filtration is defined as the process of separating solids from a fluid while it is passing through a porous medium. There are several key terms used in filtration. The slurry is the fluid to be filtered, which is a solid-liquid mixture. The filter is the porous medium itself. The filter cake is the accumulated solids on the filter. And the filtrate is the clear liquid obtained after passing through the filter. Before filtration, the feed often needs to be pre-treated to increase the filtration rate. Common methods of pre-treatment include heating the slurry, recrystallizing the solids, or the addition of a material called a filter aid. Filter aids are hard, strong, inert, incompressible particles with an irregular shape. They form a porous, permeable, rigid lattice structure that allows liquid to pass through but retains solid particles. They are used to improve the filtration of highly compressible filter cakes or when filtering small amounts of finely divided solids. Common materials used as filter aids include cellulose fibers, diatomaceous material, expanded perlite, charcoal, and paper pulp. The filter medium is a crucial component. It promotes the formation of the filter cake and supports it once formed, effectively becoming the primary filtering surface. It should be non-toxic, chemically inert, and can be flexible or rigid. Often it is a woven cloth made of cotton, wool, silk, or synthetic materials like nylon, polyester, polyacrylonitrile, polyvinyl chloride, polyvinylidene chloride, polyethylene, or polytetrafluoroethylene. Filtration has many applications in the dairy industry. It is used for the filtration of raw milk at the dump tank in milk collection or chilling centers. It occurs during processing while milk passes through a pasteurizer. It is used in the reconstitution of milk powder. It helps remove ghee residues from ghee. It is essential for the separation of whey during cheese manufacture and during the preparation of channa. The applications extend to other areas as well. For water, filtration provides protection for equipment like seals, pistons, and nozzles from abrasion and blockage. It acts as a particle trap after UV resins and carbon treatments and protects RO membranes. For air and gas, it supplies aseptic air for packaging and sterile air for overpressure systems. It ensures clean, particulate-free air for processes like gas sparging and product conveying. For CIP fluids and brine, it allows for clarification, recycling, and microbial control. For additives and ingredients in the milk and whey phase, it is used for clarification, microbial control, and aseptic applications. For incoming milk, it can be used for bacteria removal, particle removal from concentrates, and in milk fractionation. Filtration can be classified based on how particulate matter is filtered. The three types are surface filtration, depth filtration, and cake filtration. In surface filtration, particulate matter is retained solely on the surface of the filter. In depth filtration, particulate matter is retained not only on the surface, but also within the inside pores of the filter medium. In cake filtration, the cake that accumulates on the surface of the filter itself acts as the filter medium for subsequent flow. Another way to classify filtration is based on the solid content. Cake filtration is used for feeds with a high solid content. Clarification is used for feeds with a low solid content. Microfiltration is used to remove very fine solid particles. We can also classify filtration based on membrane pore size. This includes reverse osmosis or RO, which has the smallest pores, nanofiltration, NF, ultrafiltration UF, and microfiltration MF, which has the largest pores. These are used to separate everything from water and minerals to sugars, proteins, and bacteria. Furthermore, filtration can be classified based on the type of force used. The main types are pressure filtration, vacuum filtration, and centrifugal filtration. The theory of filtration revolves around two basic quantities, the filtration rate and the pressure drop across the filter. The rate of filtration depends on the fluid properties, volume 5, viscosity micro, and solids content S, passing through the filter medium of area A. The flow experiences a resistance R and is driven by a pressure differential delta P. As solids are removed and accumulate, the resistance to flow increases throughout the process. The total pressure drop, delta P, is the sum of the pressure drop through the filter medium, delta P_M, and the pressure drop through the filter cake, delta P_C. Several factors affect the filtration rate. These include the volume of filtered fluid, V, its viscosity, micro, its solids content, S, the surface area of the filter, A, the total resistance, R, the pressure drop, delta P, the thickness of the accumulated solids in the filter cake, L_C, and the fictitious thickness of the filter material itself, L. The rate of filtration can be thought of as the driving force divided by the resistance. The driving force is the pressure required to move the fluid, which is A times delta P. The resistance is R. This gives us the equation dV dt equals A times delta P divided by R. The overall resistance, R, is given by the formula R equals micro times R prime times the quantity L_C plus L. Here micro is the viscosity of the fluid. R prime is the specific resistance of the filter cake, a property of the particles. L_C is the thickness of the cake. And L is the fictitious thickness of the filter medium. The thickness of the accumulated solids, L_C, can be calculated. It is equal to the solids content, S, times the volume that has passed through, V, divided by the cross-sectional area, A. By substituting this expression for L_C into the resistance equation, we get R equals micro times R prime times the quantity SV over A plus L. Substituting this new R into the rate equation gives us our governing equation. dV dt equals A delta P divided by the quantity micro times R prime times the quantity SV over A plus L. The filtration process typically occurs in two phases. The first is constant rate filtration, which occurs during the early stages for a time t1. The second is constant pressure filtration, which occurs during the final stages for a time Tp. For constant rate filtration, we can integrate the governing equation. Rearranging it allows us to determine the pressure drop as a function of the filtration rate. The equation becomes delta P equals micro times R prime divided by A squared times T1, multiplied by the quantity SV squared plus LAV. If the thickness of the filter medium, L, is considered negligible, this simplifies to delta P equals micro times R prime times S times V squared divided by A squared times T1. For constant pressure filtration, we integrate the governing equation with respect to volume and time. After rearranging, we get an equation that relates the time, Tp, to the volume filtered. If L is assumed to be negligible, the equation simplifies to Tp equals micro times R prime times S times V squared divided by 2 times A squared times delta P. To summarize the theory, the rate is driving force over resistance. The resistance depends on viscosity, specific resistance, and the combined thickness of the cake and medium. The governing equation combines all these factors. We have specific integrated forms for both constant rate and constant pressure filtration scenarios. Now let's look at the equipment used for filtration. All filtration equipment must provide mechanical support for the filter medium, have flow accesses to and from the filter medium, and include a provision for removing the accumulated filter cake. The main types of filtration equipment are the plate and frame press filter, the rotary drum filter, and the centrifugal filter. The plate and frame press filter is a type of pressure filter. It consists of a series of plates and frames sandwiched together alternately and supported on vertical plates. A cloth filter medium is supported on a corrugated material. It has ports for the slurry to enter and the filtrate to exit. This slide shows a diagram of a plate and frame press filter. Here is a photograph of the equipment. In terms of how it works, the feed liquor is pumped into the press. The liquid passes through the filter cloths and flows down the grooved surfaces of the plates. It drains through an outlet channel in the base of each plate. A layer of cake builds up on the cloths until the space between the plates is completely filled. Air is sometimes used to dry the cake. Finally, the press is dismantled and the solid cake is removed. This slide shows a graph related to the performance, likely plotting something like gallons per hour. The plate and frame filter has several advantages. Its construction is very simple and can use a wide variety of materials. It provides a large filtering area in a relatively small floor space. It is versatile, as capacity can be varied by changing the frame thickness and number. It can handle considerable pressure differences. Efficient washing of the cake is possible, and its operation is open. There are no moving parts, cloths are easily replaced, and any leaks are visible and won't contaminate the filtrate. However, it also has disadvantages. It is a batch filter, which can be time-consuming. It is an expensive piece of equipment, and the costs of emptying, labor, and cloth wear and tear are high. Operation is critical. The frames must be completely full, otherwise washing is inefficient and cake removal becomes difficult. Next, we have the rotary drum filter, which is a continuous filtration system. This slide shows an image of a rotary drum filter. Another type is the centrifugal filter, which uses rotational force to drive the filtration process. This slide shows an image of a centrifugal filter. We will now return to the principles of centrifugal separation, building on our earlier discussion. The basis for centrifugal separation can be the size, shape, or density of the particles. A key factor is specific gravity. For example, fat has a specific gravity of 0.93, skim milk is 1.036, and whole milk ranges from 1.028 to 1.032, depending on its composition. Stokes' law governs the sedimentation of a particle moving through a viscous liquid. The particle attains a constant velocity. This rate is very slow for particles with a density close to the liquid, for very small particles, or when the liquid viscosity is high. The graph shows how sedimentation rate is affected by liquid viscosity, particle density, and particle size. The sedimentation velocity is dramatically increased in a centrifuge. By replacing gravitational acceleration with centrifugal acceleration, which can be thousands of times greater, the sedimentation rate becomes thousands of times faster. The formula for centrifugal sedimentation velocity is v_c equals d squared times the quantity ρ_p minus ρ_L divided by 18 times eta, all multiplied by r times omega squared. The centrifugal force on a particle rotating in a circular path is given by f_c equals m times r times omega squared, where m is mass, r is radius, and omega is angular velocity. Since omega can also be expressed as v divided by r, where v is tangential velocity, the force can also be written as f_c equals m versus square divided by r. It can also be expressed in terms of rotational speed in rpm/n as f_c equals 0.011 times m times r times n squared. To understand the separation in a centrifuge, consider a thin differential cylinder of thickness dr and height b. The differential centrifugal force across thickness dr is df_c equals dm times r times omega squared, where dm is the mass of the differential cylinder. The mass dm is equal to 2 pi times ρ times r times b times dr, where ρ is the liquid density. The area over which this force acts is 2 pi rb. Therefore, the differential pressure P equals df_c by A, which simplifies to ρ times omega tau, the power of 2 times r times dr. To find the pressure difference between two radii, r1 and r2, we integrate this equation. The result ISP2 minus P1 equals ρ times omega tau, the power of 2 times r2 to the power of 2 minus r1 to the power of 2. Now consider the bowl of a vertical continuous liquid centrifuge. Feed enters near the axis. Heavier liquid A discharges through a top opening at radius r1, and lighter liquid B discharges through an opening at radius r2. At some radius r_n, the two phases separate. For the system to be in hydrostatic balance, the pressures of each component must be equal at radius r_n. Setting the pressure equations for each liquid equal and solving gives USR_n to the power of 2 equals ρ_a times r1 to the power of 2 minus ρ_b times r2 to the power of 2 by. A key component in a centrifugal separator is the disc stack, which contains distribution holes for the liquid. This diagram shows the internal parts of a separator. Incoming milk enters and is separated into skim milk and cream. Key components include the outlet pumps, bowl hood, distribution holes, disc stack, lock ring, distributor, sliding bowl bottom, bowl body, and hollow bowl spindle. Separation occurs in the channels between the discs. Liquid enters at the outer edge, R1, and leaves at the inner edge, R2, continuing to the outlet. During this passage, particles settle outward towards the upper disc. The concept of a limit particle is important. This is a particle that, if it starts from the least favorable position, point A, will just barely reach the upper disc at point B. All particles larger than this limit particle will be separated if they start in the shaded area between the discs. This slide illustrates how milk enters the disc stack through distribution holes. Solids are ejected by briefly opening the sedimentation space at the periphery of the bowl. The sectional view shows the separation of fat globules from the skim milk. The flow rate of milk, Q, through the discs is given by a complex formula involving a correction factor, C, the number of discs Z, the disc angle alpha, the outer and inner radii r_o and r_n, the rotational speed n, the limiting diameter of fat globules d, the density difference delta rho, and the absolute viscosity mu. The energy requirement for a centrifuge involves the kinetic energy of the rotating body, which is W equals 1/2 times I times omega squared. I is the moment of inertia, which is the sum of m times r squared for all mass elements. The moment of inertia is a measure of a body's resistance to angular acceleration. For an object with symmetry, it is a fraction of what it would be if all mass were at the outer radius. It is calculated as the sum of the products of each element's mass and the square of its distance from the axis. The energy required to start up the machine is given by W equals P2, the power of 3 times rho underscore B, times n to the power of 2 times R underscore O2, the power of 4 minus R underscore e to the power of 4, times L, where rho underscore B is the density of the bowl, and L is the length where the mass is concentrated. Finally, the power required to start the separator is P equals Wt, where T is the time to reach running speed. The power required to accelerate the process to a certain peripheral velocity, ISP, equals 1/2 times m times 2 pi nr underscore I squared. Thank you for joining this intensive class on filtration and centrifugal theory. We covered the fundamental principles, the mathematical models governing filtration rates, the different types of equipment, and the detailed physics behind centrifugal separation. This knowledge is crucial for designing and operating efficient separation processes in any dairy plant. Thank you. See you in the next class.